All right, 7.6 B as in Bravo, College Algebra. We are on example 3 with market equilibrium. They give us the problems. They give us the equations. So they're using a P and a Q instead of an X and a Y. And you could use an X and a Y if you want. It doesn't really matter. And they also give us a second equation. Okay, where P is in the price of dollars and Q is in is numbers. So P equals price and Q equals the number in, well, they give us the number in hundreds. So the number of objects, units they call them, whatever the heck a unit is there. All right, so they give this to you. And for the most part, all we're going to do is take this equation, and whenever we see a P, we're going to put 1200 minus 60Q in its place. And then we're going to set it equal to 0. So Q squared plus 60Q minus 396 equals 0. So what we did is we took both of these numbers and moved them over here by changing signs and combined like terms. And then all you're doing is you're going to see if you can factor it. In this case, you can factor it. Two numbers multiplied together give you 396, added together give you positive 60. So my Q is negative 66 and my other Q is 6. Okay, and this is where the story problems make rules about what works and what doesn't. Obviously this doesn't work because Q is the number in hundreds and we can't have a negative 66 units. So therefore 6 is the one that works, and they're in hundreds, so 600 units is the one that works. And then we take our 6 and put it in here for Q. So 36 plus 804 is $840 is what the cost is for 600 units. That's the equilibrium. All right, so example 4, they give you an opportunity to solve a nonlinear system graphically, and really all you need to do is put those two equations in there and you'll get a graph similar to, well, it should be exactly like figure 7.27, and you're good to go. You just look there and figure out what your two x values are and your two y values, where, you know, those two graphs cross, and then you can pick your answer there. Okay, so example 5, constructing a box. I always got rather annoyed with these constructing a box kind of things because, you know, it's like, okay, why are you giving me something that isn't even really real life here? But anyway, an open box with a square base is to be constructed so that the area of the material used is 300 square centimeters. So that's how much material I'm using, 300 square centimeters. The volume of the box is 500 cubic centimeters. What are the dimensions of the box? So we have X, Y, Z. Length times width times height, which I suppose I could use that. Okay, so the area of the base is x squared, and the area of each of the four sides is length times width, and and because there's four sides, we get then 300. And reason that we have one base and four sides and not a top is because it says at the beginning it's an open box, so we don't have a lid. We just have we have one base and then the four sides without a top. All right, so the volume of the box is going to be x squared y equals 500. So that gives us the system of our first equation and then our volume. And I got the volume because I know the area of the base is x squared. Talked about that up here. Area of the base is x squared, and then you multiply the area of the base times its height, and that's where our 500 comes from. Okay, so there is our equation there, or our system of equations here. Make the cool little parentheses there, or braces, or whatever they're called. And you solve from there. I would, again, substitute. And then whenever I see a y, I'm going to put that in its place. So I end up with x squared plus 4x times that right there. Okay? And then we just go ahead and solve this. So we just multiply what we can. Okay? And I know that because I have an x squared here and an x here, I can cancel that x with one of these x's. Whoops, let's get this stuff out of the way here. So now I've got x squared plus 2,000 over x equals 300. Alright, so this one is a little bit tough to solve algebraically. So we solved the original system by graphing. You can use your graphing calculator and solve that. You know, the way you would end up graphing it, I guess, or solving it algebraically is multiply the whole thing by x, but that would give you an x cubed, which could be a hassle. That's about the only option you have there, unless you put both of these over x and this over x, and you could combine things, but yeah, you're going to end up with kind of a mess there. So just graphing it and finding out where the two graphs cross from this equation right here. Put that in your graphing calculator and it'll give you the answer real quick and easy. Alright, so last thing we're going to look at would be oil production. And they give you basically, you know, the two equations there. So I guess you really don't have to even read everything in the story problem. But it would be good to read it just to make sure you know what you're doing. Following functions with x equal to the number of years after 2010 and y equal to the number of millions of barrels of oil per day give forecasts of oil production for the United States and Saudi Arabia from 2011 to 2025. Use technology to find the years in which U.S. production will equal that of Saudi Arabia using this model. Alright, so you're just going to plug those two equations in, and it's going to give you two graphs. Okay, so notice that the values of x corresponding, I'm looking at figure 7.31a and b, and the values of x correspond to the number of years after 2010. Thus, according to this model, U.S. oil production will equal that of Saudi Arabia in 2017, and then it will change. But then again, in 2026, the lines cross again. So I can't tell which one is red, is that whether that's Saudi Arabia or the U.S. But in any case, the lines cross in 2017 and then again in 2026. So that is how you do that. You just plug those numbers in. It gives you a cool little graph, and you get the answer there. All right, so that is it for 7.6. We'll be heading for the last chapter of the book in the next lesson.